Let's start by doing a little bit of a review. In the last lecture, we had started talking about backpropagation, right? And I mentioned that the backpropagation, first of all, consists of the gradient descent algorithm, right? And I showed you the following gradient descent algorithm. Let me see if I can maximize that. So this was the algorithm. This was the example that we had seen last week. And let's just quickly take a look at that. Maybe somebody can explain what this diagram tells us. How does the gradient descent algorithm work? Right. Right. So this is not really telling you whether it's going to be a global minimum, rather, because this is represented by the error function over here. Okay, so let me. So this is represented by the error function here, and the error function is basically can also be called the loss. All right, and this needs to be minimized. So what we're trying to do is we're trying to find the minimum point, and the gradient descent algorithm doesn't necessarily in this particular example, it doesn't seem to be finding the global minimum. It's simply trying to find, if you start off with a particular point over here, it's simply trying to find the local minimum, all right? And it starts off over here and it finds the next point is simply given by this particular equation, which we looked at last time. Wn plus 1 is the previous value of the particular weight and minus the a learning rate multiplied by the gradient, right? Now, one thing I didn't specifically state last time was where is the gradient determined? If you're looking over here, and if you, let's say you're calculating Wn plus 1, right? So is the gradient at Wn plus 1 or is the gradient at Wn? At Wn at the previous value, right? So when you're looking at this particular point, you need to find out where the next value is. So naturally, you find the gradient at this particular point, okay? So this is just a little addition over here that W give the gradient at the particular point W is equal to Wn. This is how we write it, okay? So this simply in an iterative way will find you, hopefully if you do enough iterations, it'll find you the local minimum. Now, any of you who've tried the homework so far? No, so it's too early for me to give you any hints. So look at this. Just a small hint. The equation that I've given you is a fourth order polynomial. Now, would you normally have an equation for the loss equation? I've given you in the homework, I've actually given you the equation for the error, right? And I've given you as an equation like something like 500 minus x power something plus dot 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 x power all the way up to 4. So how many minimum and maximum do you think it has? If it's a quadratic equation, it's x squared, let's say, will it have 1 or 2? How many minimum or maximum will it have? It will have 1, right? Because the derivative will give you one solution, which means that there's only one point where it actually, the slope comes out to be 0. If it's a fourth order polynomial, x to the power 4, how many minimum or maximum will it have? It'll have 3, all right? So it could be either 2 maxima and 1 minima. It could be 2 minima or 1 maxima, right? That depends on the actual values of the coefficients of x for all the powers of x. So that's something that you don't need to immediately figure out, but I've asked you to apply the equation, apply the gradient descent algorithm, and then try to see, and not just to find out for one particular value of W0, I've asked you to do it for several values, right? Pick it randomly over the certain range. And then see if you get the minimum point. If you get to a particular, you converge to a particular solution, first of all. And if you converge, is it always converging to the same point? Okay. And if it's not, then you might be able to figure out, okay, there seems to be maybe more than one minimum. All right. And then at the end, I've asked you to plot it, and then you see the entire curve. And then you can see, okay, this is what we were trying to solve. Okay, so this is how this particular problem is framed. Now, I've called this equation 1. So this is the first equation that we've come across, and it's an important equation because now, as we go through backpropagation, we'll come across other equations, and then we'll refer back to this equation. Okay, so what is this equation basically telling us? That in an iterative way, how do you find the weights of a particular, for let's say it could be a multi-layered perceptron, or it could be a single perceptron. How do you determine the weights? And now we know that the weights are determined by looking at the error. Okay, so now let's take a particular example, again looking at our previous example where we had the single perceptron. So we had this particular example where we had x1, x2, you had the weights w1, w2, and you had y, and in between I indicated a value of f. What was the equation of f? It was simply a summation of wi xi, and then of course there's also a bias, right? So this was the equation. This is also referred to as forward equations. Okay, this is a forward equation. Why? Because as you'll notice that it is going forward. Then there'll also be backward equations which will be used in the backpropagation algorithm. All right, and y is some function, some nonlinear activation function of f, right? This I'm going to for this lecture, I'm going to assume that it is given by sigma of f. Now, sigma of f, as we talked about earlier, is does anybody remember what I referred to it? What is sigma of f? Or this function? It's a sigmoid function, right? So this is the sigmoid, and it looks something like this. All right, and the equation for sigma of f was given by 1 upon 1 plus e to the power minus f, and as f goes to plus infinity, it goes to 1, it goes to minus infinity, it goes to 0, and when f is equal to 0, this is equal to 0.5. Okay, so this was the equation. Now the main question is that if you look at the previous equation, it says Wn plus 1. So for any one of these equations, for any one of these weights, we now need to determine in an iterative way how would it actually be determined. All right. In the example in one of the first lectures I gave you, I said let's pick a particular value, and we looked at the example of dogs and cats and the classification example, and we said, okay, if you plug in this particular values of weights and bias, it is able to do a linear separation, right? But the question was, how did we come across that? So the issue is, how do we come across this? And what we're going to do is we're going to use equation number 1, which says Wn plus 1 is equal to Wn minus the learning rate times the rate at which the slope with respect to W. Okay. Now notice that the slope is with respect to W, and if you're trying to find out for Wi, then we would need to have the partial derivative. This is called a partial derivative with respect to Wi, right? So for W2, it would be the partial derivative with respect to W2, and so on. Now, how do you think we're going to find out the new value of Bn plus 1? Sometimes this pen doesn't work properly. Let me see why it's not working properly. Okay. So So if you want to calculate Bn plus 1, I hope this is visible to everybody. I'm not going to maximize it because then the pen doesn't work properly. Computer is acting a little slow. What would be the equation for Bn plus 1? In other words, I said that the weights can be iteratively calculated, but the bias also has to be iteratively calculated, right? We have three constants. We've got the W1, W2, and the bias. All three of them have to be iteratively calculated, right? So, and the bias is telling you where exactly is the line. Is it to the right or left and so on. So the bias also has to be iteratively calculated. What's the equation for the bias going to be? Can somebody tell me? So let's say you start off with a particular value of B. So how do you calculate Bn plus 1? It's going to be minus, and then we could use the same learning rate, all right? And then what's the rest of it? Speak up a little bit. The rate of change of E hat, in other words, the loss, because overall we're trying to minimize the loss. So we still have the same equation for loss, but now it's going to be with respect to B, right? So stop for prayers in a few minutes. So it has to be with respect to the parameter that you're trying to optimize. Okay. Now the main question remains that how do you find out this particular value, right? How do you find the rate of change of the loss function with respect to a particular value? In this particular example, how do you find out the rate of change of the loss function with respect to a particular W? How do you think we can do that? Any ideas? Now, if the equation was given as I had given it in the homework assignment as a quadratic or a polynomial equation, then obviously it's very easy to solve, right? You can simply take the derivative. But this is, the loss function is going to be, as I showed you in one of the examples, it could be extremely complex. So we don't actually know what the loss equation is. So how do you find out the derivative with respect to a particular value? जी आप कुछ कह रहे थे. Any ideas? How do you find the derivative? First of all, what's the equation for the loss function? So E hat is equal to Y hat minus Y, right? And by the way, if you have lots of Y's, for example, in the dogs and cats example, it wasn't just one single data point, right? We had 6, 7 data points. So in that case, it's going to be, is it going to be simply a single Y hat minus Y, or would you want to minimize over all the possible data points, right? So you'd want to get the average. So somehow you would probably do something like this, not just the squared, but you would want to probably have something like summation, right? So it would be a summation over all possible values of phi. So if you had, in the example that I had earlier, you had 6, 3 cats and 3 dogs, you would sum it over 6 points, but it could be, 6 million, depending on how much data do you have, okay? So this could be a very big sum, but let's assume for the time being that we're going to make it simple, and we simply is going to assume that E hat is simply equal to a single point, Y minus Y hat. Sorry, Y hat minus Y, and we're looking at the mean squared error, okay? And a lot of times we're not going to be really concerned with the constants, okay? Divided by, whether it's divided by K or divided by 2 or whatever, because the constants are going to eventually get merged into the learning rate, okay? So, so E hat is known. Now, how do you find out E, the derivative, the partial derivative of E with respect to W? Okay. Any thoughts on that? So we try to find the partial derivative. We try to find this particular value, right? The derivative of the loss function, right, with respect to W. We're trying to find this because this is the fundamental equation. This is the equation number one, right? So how we know what the previous value of Wn is. What did we do with the learning rate? We picked it out of a hat, right? We just took a particular example, and then we're going to see if it's too big or too small. If it's too big, it's diverging. If it's too small, it might be taking for too long, and so we might play around with that. But we need to find out the rate of change of the loss function with respect to the weight. Okay, and we have an equation of the loss function with respect to y, but we don't know what it is with respect to x or with respect to w. So how can you find the rate of change of E hat with respect to w, let's say w1? How do you do that? Sorry? Okay, so yes, so now the point is that we need to get this equation in terms of, if you want to take a derivative with respect to w, then this equation has to be in terms of w, first of all, right? And then we've got to, maybe then we can look further. So let's see if we can write this equation in terms of w. So what would the equation be? So we've got E hat is equal to y hat minus y, right? Y hat, what do we know about y hat? Is that a variable or is it fixed? What exactly is y hat? It's our desired value, right? So the desired value is actually a label, okay? So that's fixed, okay? Y hat is fixed. Y is being generated based on the data in the neural network, okay? And so that's a variable. So y was given by what? If you look at the previous equation, what was the equation for y in terms of the rest of it? It's based on a activation function, right? So we've got that over here, okay? So let's write y in terms of the, so it can be simply written as y is equal to sigma of f, okay? So it's y is equal to sigma of f. However, f now in turn is written in terms of x, and this is simply w1, w sub I, so we've got plus b, all right? Sorry? So this is not a power, this is, yeah? GG. So what you're saying is that actually this is an equation which looks like this, 1 plus e to the power minus f, right? आपका ये सवाल है ना कि actually this is sigma of f which is actually equal to 1 plus e to the power minus f. So we've got all the equations, and essentially this can be written as, sorry, I forgot the squared, all right? That's a mean squared error. So remember, it's not just the absolute error, it's the mean squared error, because the absolute error won't make sense. It has plus and minus values. So we've got all of these equations. We need to find out what is E hat upon with respect to W. Now, we've got it in terms of y hat minus y squared, and y itself is a function of f, and f itself is a function of w. So ultimately, we can express it as a function of w. And once you've done that, then can we take the derivative? Right? All of you have studied calculus, right? So then we can take the derivative. Okay, G. बहुत अच्छे सवाल है. So what about x? Now the point is that we are taking the derivative with respect to W. Okay. So as far as this particular equation is concerned, what do you think the answer is to aapka naam kya hai? Sorry? Babar, right. So what do you think is the answer to Babar's question? Will X be considered as a constant when you're taking the derivative? It will be, right? Because now we're looking at the rate of change with respect to W. Everything else can be considered as constant, or at least as far as the input is concerned, we'll consider it as a constant. Okay. Now the question is, so you've got an equation which looks a little bit messy. It has, if you start to write it out, it'll be pretty messy. So even if I try to write it out, because there's this sigmoid equation which is pretty messy, right? So it will actually look something like, let me try to write it down. 1 hat minus y 1 upon 1 plus e to the power minus, and f actually is summation of wi xi plus b, right? So this is the whole equation, and we need to take the derivative with respect to w. Okay, so it looks kind of messy, and it's not clear how we can immediately solve it. Now, remember when you had an equation something like, let's say x plus 4 to the power of 3, and we need to take the derivative of this, okay? How would we do that? Let's say this is y, and we need to take dy by dx. How would you do that? First take the derivative of the whole thing, and then, so we used to use this something called a chain rule, right? So basically the chain rule says that in this particular case, it would be 3 times 2x plus, let's say whatever, this is 4, and then we take the derivative of the inside, which comes out to be 2. Okay, so this is what the answer is. And we basically applying the chain rule, okay? So the chain rule basically says that if y is a function, let's say f of x, right? And y is a function of x, let's say in this particular case, y is a function of g, and g is in turn a function of x, okay? So if we want to take the derivative of y with respect to x, what we can do is take the derivative of f with respect to, or in this case, actually I've written it opposite, but it doesn't matter. We take the derivative of f with respect to g, right? And then we take the derivative of g with respect to x, okay? So this is a very straightforward chain rule. In fact, if you take this further, if you say that y is a function f1, f2, and f3 of x, all right? And we want to take the derivative of dy by dx, then what can we do? We take dy by df1, right, times df1, derivative of f1 with respect to f2, and so on, derivative of f2 with respect to f3, and then the derivative of f3 with respect to x. So this is the standard chain rule. Hopefully this is jogged your memory, you've studied this in calculus, okay? So let's apply this, and this is about the extent of math we're going to do. In case any of you are getting scared, this is some of the simple math that we'll do, and this is important because you need to understand some of the fundamentals, and then we as the course progresses, the maths will probably become a little simpler, and we'll be looking more at the actual applications, okay? So now going back to this particular equation, okay? How can we take the derivative? So we come back to this particular case, and now we're trying to find out what is the derivative of E hat with respect to dw. So what we can do is we can take the derivative with respect to y, okay, because E hat is a function of y, okay, and then we can take the derivative of y with respect to f, okay, and then we can take the derivative of f with respect to w, right? And so that's how we can solve our little problem. So let's try to do that. What is the derivative of E hat with respect to y? Remember, this is simply y hat minus y the whole squared with respect to y. What is this? 2 times y hat minus y, okay, times minus 1. So because you take the derivative of minus y, you get minus 1, all right? Now, this is simply what? Y hat minus y can be referred to as the error, okay? And that's why I call this E hat, because this is the mean squared error, and this is the absolute value of the error, okay? So this comes out to be minus 2 error, okay, the absolute error, okay? So we found out what the first term in this equation is, which is simply this particular value, okay? जी. हाँ, तो उसकी y hat fixed है, so this could be a constant. So जब ये constant है, तो that is, it is not a function of y. So that's why when you're differentiating it, I ignored it. When I took this particular value, I differentiated the external 2 times this particular function, and then I took the derivative of y hat minus y. उसमें y hat का derivative 0 बन जाएगा, और minus y का derivative with respect to y will become 1, will become minus 1. ठीक है. आपका थोड़ा सा ऊंचा आपको बोलना पड़ेगा. I can't hear you properly. हाँ, ठीक है. हाँ, yeah. Because remember, how did we do the derivative? When we had the derivative of this 2x plus 4 the whole cube, we took the derivative 3 times, बल्कि यहाँ पर एक square आना चाहिए. The power becomes 1. लेकिन ये equation तो फिर भी रहता है ना? Okay. तो यहाँ पर ये equation है. So this is still coming in. Okay. इसका power यहाँ पर आ गया. The power over here cancels out, comes over here. The power becomes reduced by 1. Y hat minus y will still be there, multiplied by the derivative of the inside. ठीक है. So आपका ये minus 2e आ गया, which is the derivative with respect to y. This is the first term. Okay. So far, so good. So far, good. Now, how do we get the derivative of the second term? Now, the second term is y is equal to 1 upon 1 minus 1 plus e to the power minus f. So how do you take the derivative of this? So you can do it. So it's a little complex, but I won't waste your time to do this. Interestingly, the solution is very simple. The solution is sigma times 1 minus sigma. In other words, the equation, the solution is 1 plus e to the power minus f, this is sigma, times 1 minus 1 upon 1 plus e to the power minus f, okay? And the derivation is kind of long. I don't want to bother you with that, but if anybody of you are interested, you can actually do the derivative and you can find out what the solution is, what the equation is, okay? And this is one of the nice properties of the sigmoid equation, okay? So the sigmoid equation, which I showed you over here, what if you had the ReLU function? The ReLU function, remember, it looked something like this. It looked like this, okay? So if sigma of, if the nonlinear activation function was this particular equation, all right, which was the ReLU, what do you think the derivative of this would be? Okay, so the derivative over here would be constant. Absolutely right. The derivative over here in this particular area would also be constant, which would basically be zero. Well, over here it will be zero. Over here it will be basically be the slope of this. So if it's slope of +1, the slope will be 1. Is that it? So it's piecewise the derivative. What about, is there some non-linearity somewhere? So is there a problem over here? What would be the derivative over here? You can't calculate it, right? Because the derivative over here changes sharply. So it will actually be plus infinity, okay, because it's immediately sharp. So you can't really take a derivative of an equation which looks something like this. If you have max 0 comma f, you can't really take a derivative of that, okay, because it's one of those equations which doesn't have a simple derivative. However, the sigmoid is used interestingly because you can take the derivative, okay? Simply because the equation over here is something that does have a derivative, okay? So, so fortunately for us, as I said earlier, in this particular example, in this today, I'm going to use this particular equation. So I'm going to use that the nonlinear activation function. I'm going to, for sake of simplicity, I'm going to use an equation, a sigmoid equation, which does have a derivative. Okay. So coming back over here, we have a solution for the rate of change of y with respect to f as well. We've done the first one, and now we've also done the second one, which is simply whatever the value of sigma is times 1 minus sigma. Okay, and remember sigma is also a value, always a value between 0 and 1. So this will also be a value between 0 and 1. Okay, both of them will be non-negative. All right. What about the last term? df by dw. Can somebody solve that for me? What's the solution for that? Right, by now you should, it's summation of wi xi plus a constant b. So if you take the derivative of that, what do you get? Now remember, this is with respect to a particular value, right? We're taking a derivative with respect to one of the wi's. So now what's the answer? Think of it this way. You're taking the derivative with respect to w1 of w1 x1 plus w2 x2 plus b. What's the answer of this? Sorry? Summation of x, x1, right? So aapka naam kya hai? Mudassir. So Mudassir has got the right answer. It's simply x1, right? Because the rest of them, as far as w1 are concerned, are constants. Okay, so it will simply represent x1. Okay, it's simply linear in terms of x1. So when you take the derivative with respect to w1, you get x1. Okay, and that comes back to your question whether x1 is treated as a constant or not. Yes, it is treated as a constant, and interestingly, it comes out as part of the result. Okay, so if I write this over here, what is the answer? We've got minus 2e, not e hat, e, the absolute error, multiplied by sigma times 1 minus sigma, multiplied by x1. Okay, so so we've been able to calculate the value of the derivative, the derivative of the loss function with respect to a particular value, which is, let's say in this particular case, with respect to w1. All right. Now, once we've got that, have we solved the equation? So going back over here, we wanted to solve this particular equation, right? Now we had Wn was known, the learning rate was known, and this was the term which was unknown. And now we found this in terms of the parameters which are all known. Okay, so now we can calculate Wn plus 1. Okay, so we can now calculate Wn plus 1. I is equal to Wn I minus R times the learning rate. Now, learning rate multiplied by, and what is the answer? Does somebody remember that from the previous page? It was minus 2e sigma 1 minus sigma times xi. Okay, so I'm writing it in terms of I, so it'll be xi. Okay, so far so good. This can be slightly simplified. This will become a positive. The 2 is not important because the learning rate, it can be merged into that. Okay, that's already a constant which we're going to play around with. So we can simply write it as Wn(i) plus e sigma 1 minus sigma xi. Okay. G? Sorry, the learning rate. So got the learning rate here. Okay. Now, can somebody guess what the equation for Bn plus 1 would be? We already know it's the previous value. Now, if you look at this equation, if you try to find the rate of change of E hat with respect to, instead of W over here, let's replace that with B. Okay. What's going to change in this equation? Is this going to change? No. Is this going to change? This is not going to change. Is this going to change? Yes. Now, instead of taking the rate of change with respect to W, we're taking the rate of change with respect to B. So what do you think this value is going to become? It's going to become 1. All right. So now you can guess just by looking at this, what is the equation for B going to be? Plus R E sigma 1 minus sigma times 1, right? Because instead of xi, we're going to replace that with a 1 because the rate of change of f with respect to B is simply 1 because B itself is just a constant. Okay. So I hope that is clear. We're taking the we're taking the derivative over here with respect to B, and when you take the derivative with respect to B of this equation, it simply becomes a constant 1. Okay, it's the coefficient of B, which is actually 1. Okay. So now we've actually solved the entire system. The original equation was we wanted to find out how to update W1. We know that. How to iteratively improve W2. We've got that, and we've got a solution for B as well. How do we iteratively update B? As long as the nonlinear function is sigma. Okay, we haven't done that for a ReLU or maybe a step function, but we know how to do that for a simple sigmoid which is differentiable. Okay. Right.
Sir, I have a question from previous class.
G, who is this? I'm sorry.
Naman.
Naman. Right. G, go ahead.
जी सर, क्वेश्चन ये है कि लास्ट टाइम हमने जो डिस्कस किया था कि जो न्यूरॉन्स हैं, तो न्यूरॉन्स में जो है वो लीनियर
जी गो ऑन न्यूरॉन्स में आपका माइक म्यूट हो गया मेरे
सॉरी जी सॉरी सर, न्यूरॉन्स में जो है वो लीनियर इक्वेशंस फॉर्म होती है ना, सम ऑफ इक्वेशंस। तो वो
Right.
तो फर्स्ट लेयर में तो समझ में आता है कि लीनियर हमारी फीचर्स एक्सट्रैक्ट आउट हो रहे हैं। अच्छा, जब हम सेकंड लेयर में आते हैं, जब वो कंबाइन होता है, तो वो नॉन लीनियर फीचर्स किस तरह से एक्सट्रैक्ट होना शुरू हो जाते हैं?
हाँ, तो देखें, if you go back to this, hope you can see the screen. Let me make sure I've shared my screen.
Yes sir, it's visible.
Right. So देखें, जो non-linear portion है, where is that? So you write के जो आपका जो f जहाँ तक calculate हो रहा है, right? This is the linear part. But
Yes.
when you're calculating y, remember that there is a non-linear activation function. This is non-linear.
Yes sir.
Right? So जो भी आपकी non-linearity, अगर इसको हम नहीं रखें, तो the entire neural network will fail. The non-linearity, this is extremely critical portion of your neural network, the non-linear activation function. Okay? So does that
सर
answer?
लेकिन जैसे वो नॉन लीनियर तो है फंक्शन,
जी जी.
लेकिन वो कंप्लीटली जिस तरह से उसकी पावर तो कोई स्क्वायर या समथिंग नहीं हो रही ना, मल्टीप्लाई नहीं हो रही, it's still a non, it's still somehow a linear, there is a linear part in it also.
No, there's
But
no
completely sir,
linearity. Look at this. Look at this equation. You think this is linear? इस equation को देखें. Is this linear?
no sir.
This is completely non-linear, right? You can see के 1 upon 1 plus e to the power minus f. इसमें linearity तो कहीं से भी नहीं आ रही है. You understand?
Yes sir. लेकिन हम अगर रेलू को कंसिडर करते हैं,
हाँ, रेलू का अगर आप कंसिडर करते हैं तो उसमें देखें, उसमें जो आपका ये जो पोर्शन है ना, अगर आप जो अगर आपके पास मुख्तलिफ नॉन लीनियर फंक्शंस है, एक आपके पास सिग्मॉइड हो गया, राइट? उसके बाद फिर आपके पास रेल्यू हो गया, विच बेसिकली लुक्स लाइक दिस. नाउ इसमें जो नॉन लीनियरिटी, इफ यू लुक एट दिस पोर्शन and this, these two are non-linear. You understand that before a particular value of f, when f is less than 0, this is 0. You understand? This is a major non-linearity.
yes,
अगर ये equation अगर ये इस तरह जा रहा होता, तो फिर it would have been linear. यहाँ पर इस portion में it is linear, but before 0 it is non-linear. So this simple change in the activation function results in a huge, it has a big impact. Similarly, you could have a step function, right? You could have a function which goes like this. जो हमने सबसे पहले इस्तेमाल किया था. This would also, this is also non-linear. Then there are other functions as well, which we'll study later on. There is another one which looks something like this, which goes between -1 and +1. Okay, this is called the tan function. Okay, this goes between -1 and +1. So any nonlinear function, well, not any, but a lot of different nonlinear functions can be used as long as there's some nonlinearity about it. It can have a huge impact. Now the question is which nonlinear function is best, which is the easiest to apply, and so on. So as I said, the ReLU, even though it has the issue that it is non-differentiable, you can't differentiate it, but it still has, it's easy to apply. So this has been very popular in the actual industry in use in neural networks. The sigmoid function is also quite popular, all right, simply because sigmoid and tanh functions are also quite popular. The step function, I don't think I've seen it being used anywhere, but these are some of the popular functions. Okay. So Numan, does that answer your question?
Yes, sir.
ठीक है जी yeah okay good question how do you apply the gradient descent algorithm when you don't have the you don't when it's not differentiable in other words जब अगर आपने ये determine करना है this particular portion of this equation okay and one portion is non-differentiable this part is non-differentiable so how do you apply it there are techniques not everything is as simple as it seems there are techniques which can be used it can also be done part wise so you look at that particular portion jahan par ke aap apply kar rahe hain and over that particular portion if it's differentiable then for that particular area yahan par it is differentiable right yahan par it is differentiable yahan par it is non differentiable so you make sure that you're not at that particular value you then don't use that value you use some other value which is close to zero but not exactly at zero because exactly at zero it is not differentiable anything which is outside absolute zero it is differentiable okay so then it becomes a bit trickier but of course your algorithm can take care of that it can see what is the value at which you're differentiating and you just want to avoid the point where it is not differentiable okay so the calculations ultimately you've got to implement it in some algorithm right so if you're implementing it in Python or some other algorithm you'll have to look out for those things okay so let's continue where we left off so now we figured out how to solve the equations for W and B. And now let's take a look at a slightly more, complex situation. What happens for, this was a single layer perceptron, right? That was a single cell perceptron. What happens if you have a multi-layer perceptron, right? So let's take a look at this particular example. Suppose you have two layers. You've got X1 and X2, and this is feeding into another layer. And here you've got, more values. Let's say there are two layers. Okay. So the question is, how do you do this? Is this, if assuming these are all differentiable, let's say this is F over here, all right? And instead of Y, let's say this is H, okay? And this is W11, this is W21, and so on. And let's say this is let's call this W11, this is W, no, I'm not going to call this W21, this is W21, and this function here is, let's say, G, okay? And this here is ultimately Y. So the question is, can this be done? If you've got multiple layers and now आपके पास unknowns कहाँ पर है? There could be an unknown bias over here. There could be an unknown bias over here, which is C, okay? So what are the unknowns over here now? Just want to make sure that the recording is on. Okay. All right. So how would you find out, and what would be the loss over here now? Loss again, there is some y hat, which is the label, okay? And the loss function would be something like y hat minus y, again, the same thing. The only difference now is that you've got multiple layers in between. Sorry? Square, मैं हमेशा square भूल जाता हूँ. All right. So, so how do you find out the derivative? Let's say, well, first of all, what's the equation for W W11 in this case. So the previous value, W11N minus the learning rate times the derivative with respect to W11 of the loss equation, right? So far everything is simple. Now, how do we determine this? Does this become more difficult? Earlier, हमारे पास एक simple equation था, right? Now, do you think this is, you're trying to figure out that for the MLP scenario, how do we actually calculate the rate of change of the loss with respect to, and with हमें कौन-कौन से parameters का हमें update करना होगा? एक तो W11 यहाँ पर है, right? What are the parameters? Of course, the value over here, all of these values will have to be updated. The constant B over here will have to be updated. In addition, the intermediate weights will also have to be updated. Okay, so the weights over here will have to be updated as well. So let's first figure out, okay, well, this one will be a little bit easier because this is almost like the previous case. So let's try to look at this particular case. W11 को हम किस तरह iteratively update करेंगे, right? So उसकी solution again simple है कि we have to find out what the rate of change of the loss function is with respect to now. Instead of this value, we're looking at the rate of change with respect to W11. Now, any ideas again about how do we do that? आपने कहा कि simple है, तो हम chain rule again इस्तेमाल करेंगे. Now, except that the chain rule will become bigger, longer, right? So what do? We already know, we have all the equations. We've got the equation for F. We've got the equation for H. Now remember, H is the equivalent of Y earlier. Okay, the weights are W. And then we've got the equation for G, which was the equivalent of F, except now G is now the summation in the second layer. And Y is finally the application of the nonlinear activation function to G. Okay, so ये आपको समझ में आ गया. So now we can simply apply the chain rule. And if I want to do this, can somebody tell me what it would be? So this is going to be equal to what? Chain rule apply करें. The derivative E hat with respect to Y सबसे पहले होगा, उसके बाद with respect to G, very good. With respect to W2, okay. W21. Okay, उसके आगे जाएं फिर. W21 with respect to H, okay. Derivative of H with respect to F, and then derivative of F with respect to W11. Okay, does anybody think there's a problem with this equation? You think this is right? So W21 यहाँ पर आ रहा है, derivative यहाँ पर आ रहा है, right? You think this is right? And remember, what's the equation of this? We've got F, okay. उसके बाद फिर we have H, which is a function of F, all right. And then we've got G, which is a function of H, and the weights are actually constants as far as this equation is concerned. When x1 changes, the weight doesn't change. Okay, so this particular value over here is actually a constant. Okay, so ये वाला जो है, you think the step is right, and if it's not right, then what's the right equation? इनको देखें आप, इसको देखें, इसको देखें, ये देखें और ये देखें. Derivative of g with respect to h, right? So here we've gone wrong. This is the wrong part. The correct answer would be the derivative of g with respect to h. Okay, so the derivative of g with respect to the variable. Remember, h is the equivalent of y over here. So h is the variable, w is a constant. So you have to take dg by dh. Okay, so the rest of it is okay. You can remember the equation of g is in terms of h is the variable. We're taking it with respect to h, and then h with respect to f, and यहाँ पर हम with respect to constant कर रहे हैं क्योंकि that's what we're trying to determine. The only time we're actually taking a derivative with respect to a constant is the one which we're trying to determine. Okay, otherwise we're not going to be including the weights in the derivatives. Okay, so this is an important thing because in order to understand this, and as you continue to apply this, you have to understand कि कहाँ पर आपको derivatives apply करने हैं. You can't apply the derivative to the constants. Okay, so having gotten all of this, now can we simply write down the equation? So let's say कि I want to write down the equation of W11 n plus 1. I'm going to try to write it down minus. Now the rest of it is fairly similar. ये आपका क्या होगा? This will again be minus 2e, right? dy by dg क्या होगा? It will be again, it's a sigma. So this will be sigma times 1 minus sigma, all right? dg by dh क्या होगा? dg by dh. So we taking the derivative of dg with respect to h1. So it will be w21.
सर ये dy over dg जो आपने निकाला है समझ में नहीं आया.
So who is that again online? जिसने सवाल पूछा है? नमान. Okay. So देखें, ये जो हमने हटाया है dg by dw. The reason why we're not taking the rate of change of g with respect to w is because as far as this equation is concerned, the variables are h. Okay, the variable, देखें, x is a variable, it's changing. Okay, w is a constant, f is a variable, h is a variable. Okay, g is a variable and y is a variable. अगर हल्का सा x में कोई change आता है, so the constants will not change. F will immediately change because f is a function of, here's what f depends on. Depends on x.
सर ये तो मुझे समझ आ गया, तो मैं dy over dg की बात कर रहा हूँ.
dy
जो आपने sigma into 1 minus sigma.
dy upon dg आप पूछे, तो dy upon dg जो है is again sigma upon 1 minus sigma. Why? Because y, the equation for y is the same as the previous one. Okay, and if you missed this portion, we said that the rate of change of sigma with respect to dg is equal to sigma times 1 minus sigma. ये थोड़ी देर पहले हमने कवर किया था, ये अगर आपने मिस कर दिया तो ठीक है.
अच्छा.
So this is, we already know this. Where are we now? So we know this. What is dg by dh? This is important. What is dg by dh?
सर ये तो पार्शियल डिफरेंशिएशन नहीं होगी?
हाँ, तो आप इसका आंसर बताएं। पार्शियल डिफरेंशिएशन तो हर जगह आ रही है। ठीक है, आंसर बताएं। ये इक्वेशन है
W21 ही हो जाए।
W21. So this is going to be, it is the coefficient of DH. So this is the coefficient. So now if I write it down over here, it's going to be, I remember R आ जाएगा as in the past, उसके बाद फिर एक E आ जाएगा, उसके बाद फिर आपके पास sigma times 1 minus sigma, okay? And then what do you get? Then you have, what do you have after that? G? G. Sorry? थोड़ा सा आपको ऊंचा बोलना पड़ेगा। W11 के ऊपर ये जो है n is the previous value, आपकी iteration हो रही है ना, so what we're doing is this goes back to our first equation that we talked about. ये equation पर आ जाए. So this is the first equation where we're saying that we're doing an iterative equation. We are trying to find, we start with W0 and we're trying to find the next value. Okay, so the next value over here n is 0, उसके बाद पे n is equal to 1, is equal to 2 हम increment करते जा रहे हैं, right? So W2 जो है हमने किस तरह पता चलाया? W1 is basically W0, the first value of W0 over here, which was 10. We found the next value by taking W0 minus the learning rate multiplied by the gradient. ठीक है? So that's the first equation, Wn plus 1 is equal to Wn, the previous value minus the learning rate multiplied by the gradient. ठीक है? So coming back over here, this has got a little bit messy, but let's continue with this. So we're trying to find the iterative new value of W11, n plus 1 over here. This is the old value as we're iterating it. Plus, if you look at the last equation, it was simply R times error times sigma times 1 minus sigma times xi. Okay, so it's going to have a similar form. R times error times sigma times 1 minus sigma is almost the same up till here. आगे क्या difference आता है? Then there's going to be a W21. This comes in over here. Okay, the weight W21 comes in over here. उसके बाद फिर guess what will come in over here? Sigma times 1 minus sigma. Okay, because you're differentiating the nonlinear function over here. उसके बाद फिर क्या आएगा? Then x1. All right. So just by looking at this, you can actually figure out the answer. Okay. If I look at a slightly different value, so for example, if we look at, so let's do this. If we have W11 over here, sorry, x1 over here and x2 here, and this is W11, this is W21, and this is W, I think let's call this W12, and this is W21, this is F, this is G, H, and this is Y, right? So just by looking at this, can you write down the equation for, let's say, the x2 n plus 1. Okay, sorry, not x2, but W12. अब हम इसकी अगर figure out करना चाहें तो what can somebody just write down the answer for this?
सर इसकी कैलकुलेशन में W21 अपडेटेड नहीं यूज करेंगे हम पहले?
So सबसे पहले W12N the previous value, right? वो माइनस माइनस होकर के प्लस आ जाता है टाइम्स R टाइम्स दी एरर, उसके बाद फिर सिग्मा टाइम्स 1 माइनस सिग्मा, ओके, फिर W21 यहाँ पर आएगा, राइट, टाइम्स सिग्मा टाइम्स 1 minus sigma times x2. Okay, so you can just look at this and you can figure out what the equation is. Okay, so and similarly अगर आपके पास constant है b है तो you know how to do that as well. If अगर आपको इसको update करना है तो you can also do that. All right, जी हाँ, so the actual values will have to be substituted. So this sigma will actually represent sigma at that particular value. Okay, so it will be sigma of f. So when you're calculating this, these two sigmas will actually have a different value. So this will be sigma of, this is the first one. So this will be sigma of g rather. Okay, so this will be sigma of g and this will be sigma of f. So you're absolutely right, sir. It's a good question. These will be different, right, when you're calculating it. But shorthand में मैंने simply उसको sigma लिख दिया. Okay. So now you can see that this is basically all there is to the backpropagation algorithm. Okay. Now, why do you think this is called backpropagation? Backpropagation, remember I wrote down forward equations. So forward equations were going forward. Okay. The forward equation basically said, okay, if I want to write down the equation for f, this is the equation. For h, it is this equation. For g, these are all forward equations, right? But now we're writing down the equations for updating the weights and the constant. Now, why do you think it's called a backpropagation?
So इसमें feedback आ रहा है.
Okay, very good. So सबसे पहले एक तो हम we are using y hat minus y. Okay, so this is the equation for the error term. Okay, so now that we've got the error, we are now going backwards. Okay, so once we've got the error, because remember the error is over here. Okay, error आगे से अब पीछे जा रहा है. Now, do you think you're going to update W11 first, or will you update W21 first? You'll update W21. By the way, W21 की equation यहाँ पर लिख देता है just so that we know what it is. W21 n plus 1 will be W21 n plus R times E times sigma, some sigma, let's not worry about it, times so the popular word seems to be that it's going to be H. Okay, you think this is correct? Huh? Who says that's not correct? No one. So it seems like nobody is saying it's not correct. So hopefully this is correct, right? This is correct. Why is that? Because पहले हमने x1 डाला था, right? x1 was a variable. Now what we've done is we've replaced that with the variable which is h1. Okay, h1 is basically the output over here, the y. Okay, so this is how W21 is going to be calculated. Okay, which is a bit shorter, it's simpler. W21 is going to use the value over here of h. Okay, so now my earlier question was कि क्या आप W11 को पहले update करेंगे या W21 को update करेंगे पहले? Should you apply this equation or should you apply this equation first? W21, right? Why? Because W12 is actually using W21. Okay, W21 is not using W12, right? So you can see that backward equations जो back propagation is going backwards, right? So it is going in this particular direction. It's going in this direction. So once you've got the error term over here, then you figure out W21, okay? You would probably also figure out what C is, because this is in the last layer at the end of the, at the rightmost side. Once you figured out these two, then you're going to figure out the layer before that, okay? So then you figure out what W11 is, you figure out what this is, or you figure out what this is, and so on, okay? So if I were to write, if I were to show you the general algorithm, if you've got, these are all, let's say, the equations, and here, let's say you have the final value y, and I'm going to show this as an X over here. X simply means that it's what is referred to as a fully connected network, okay? Fully connected means that, let's say, these are the X's. This is X1 se lekar ke, let's say, Xn tak, all right? Then you've got a bunch of neurons over here, and these have weights, let's say, 1 se lekar ke W, N, let's say this could be P over here, because you could have different number of neurons, right? Sorry, this would be N, okay? But here you could have a different number of neurons over here. It could be P, for example, all right? Yahan par there could be different set of neurons. It could be Q over here, okay? But fully connected means that every neuron over here is connected to every other neuron over here, okay? So this is what a fully connected network would look like, okay? And we're going to simply show it with a big X, okay? That means are these neurons connected, by the way? Is this neuron connected to this neuron? Did we do that anywhere? No, we didn't do that, okay?
No, sir.
So हमने इन neurons को कभी आपस में connect नहीं किया था. This is not connected to this, okay? So only the neurons are connected to the layer, subsequent layer, okay? So this is what is referred to as a fully connected feed-forward neural network. All right, so this is a feed-forward network. G. If we do this, what happens? You create a different type of a network, and we will study that, okay? Those are called recurrent neural networks. Okay, when we get to that, we'll talk about that. But G. Exactly. Every neuron over here is only connected to every other neuron in the subsequent layer. So this is layer 1, let's say, this is layer 2, and this is all the way going up to layer N over here. So all the layer 1 neurons are connected to layer 2, or the layer 2 neurons are connected to layer 3, and so on, all the way to layer N. Okay, and at the end, you may have a single output. Now, the single output represents, if you're trying to classify, let's say, a particular, if you, for example, have, you're only trying to classify whether you have dogs or cats. Okay, binary classification aap karna cha rahe hain. But let's say you had other animals as well. Okay, so then you would have more than one Y. Okay, so you could say, for example, if it's a dog, then I want this Y to be a 1 and the other Y's to be 0. This could be Y2, let's say. Okay, so this could be Y2 and this could be Y3. So as I said, Y1 could be a dog, Y2 could be a cat, Y3 could be a goat or a horse. Okay, so if you're trying to classify one of many types, then you would need to have, you can't just have a single output. You need to have multiple outputs, all right? And if you've got 1,000 different types of images that you're trying to classify, then you would have 1,000 different, wise outputs over here. In which case, you would have a fully connected output layer as well, which means that every neuron in this particular layer would be connected to every neuron, every output as well. Okay, so every output would also be connected something like this. Okay, so Y1 would be, each Y would be more complicated. Okay, but The basic backpropagation algorithm remains the same. You take the loss over here, and the loss sometimes is generally shown as a J instead of an E hat, basically the same thing. And then you go backwards, okay? You go backwards, you find out the weight, the updates of these weights. Then based on that, you find out the updates of these weights. And based on that, you find out the updates of these weights, okay? And in each one of these cases, for each neuron, you will also have a bias, okay? So you could have a B1 over here, a B2 over here, a B3 over here, and this is generally represented as a matrix, okay? So when it becomes more complicated, it will show up as a matrix. This could be C1 over here up till CP and so on. Say that again. एक क्या sorry? एक bias जो है, yeah. नहीं, the bias is going to be different. So for every neuron, the bias will be different. Okay. So just like the weights are different for every neuron, for every connection. Okay. Remember, this represents a synapse. Remember all the way back, going out back to your biological situation. This represents a synapse, and this bias represents the change, the bias in that synapse. Okay. So yeah, so the answer is each one of these neurons will have a different bias. Okay. You could make them all the same, but then you would lose flexibility. Okay. So if you want to have a neural network which has complete, you want to have complete control over it, you would have different biases for every neuron. Okay, G. उसमें फिर change आ जाएगा. So for you to be able to find out the loss, you would have separate equations for each one of them. Okay, so that becomes more complex. But let's keep it simple right now. But I just wanted to show you that yes, multiple output भी हो सकते हैं. ज़रूरी नहीं कि output single होगा. Okay, but let's just focus on the simple case right now and try to understand that. Right. So this was the simple case where you simply had a single output. Okay. G. Go back here. Okay, so that's a good question. How do you, well, first of all, H2, is it a variable or is it one of the constants that you have to update? It's a variable, right? So उसको आपको H2 को update नहीं करना है. अगर आपका सवाल ये है कि इस particular weight को कैसे करेंगे या इस particular weight को कैसे करेंगे, that's the right question. If you ask the question कि H2 को update कैसे करेंगे, that's not the right question. So your question was? So let's say this is X3 and this is X4, okay? And now let's say this is W12 and this is W13 and this is W14. How would you calculate, how would you update W14? Aap soche. Where would the change come in? So let's say this is W21, this is W22, right? So where do you think in this equation, when you are updating, W14, where do you think in this equation the change would come in? Bajay W21 ke, because you can see it's not in the path. This guy is in the path. So ye W21 jo change ho karke kya ho jayega? W22 ho jayega, right? What else would change? X1 के बदले अब क्या हो जाएगा? अब X4 हो जाएगा, right? So you can see that you can just look at this and you can figure out how the equation would change. Basically, you have to see के path में क्या चीज़ है.
Sir, एक question है.
एक second hold कीजिए. There's a question in class. जी. जब हम अगर हमारे पास सिर्फ H2 है और आप क्या पता चलाना चाह रहे हैं? क्या चीज पता चला सके? X3 and X4. So देखें, going back to the example that we had of the cats and the dogs example, right? आपके पास यहाँ पर C1, C2, C3, D1, D2, D3 थे, right? You had an equation where your data was given. Okay, you had X1 and X2, right? You plugged in the values, the inputs were given to you. Okay, so basically in this particular example, in this particular example, you basically what you're saying is कि आपके एक set of inputs हैं, okay, and based on that set of data, you found out the output y, and based on that, you've got a label, and you're saying कि is the output correct or not. Now you find out the error because you've got a label for the output. So you find out the error, and now based on that, you want to change the neural network. You can't change the input. You're going to change the neural network. The neural network basically comprises of the weights, okay? The neural network basically says, these are the weights, and now you can modify the weights of the system so that you can have a slightly more trained network, okay? So you're not going to change the inputs. The inputs are given, output is calculated based on the weights, the label is given, okay? What you want to do is update the weights, and you want to update the biases. Okay. So are we going to update the inputs? No, the inputs are given to you. Okay. जी. जी. Sigma की जो equation है, we did that somewhere. So let me just write it over here. So sigma की equation थी 1/1 plus e to the power minus f, okay, sigma of f, all right? And if you differentiate this d sigma by df, the answer comes out to be sigma times 1 minus sigma, okay? G. W22 की, W21 की G. ओके, W22 की जो इक्वेशन निकाल 21 की, हाँ उसमें जी हाँ, this is going to be naturally sigma of G, okay, because it can't be sigma of F because वो तो पीछे है, ठीक है? There was a question online as well.
Yes sir, मेरे दो क्वेश्चंस थे.
जी.
एक तो ये क्वेश्चन है कि सर आपने W22 को 1 लिया हुआ है उस जो आपकी लास्ट स्लाइड है उसमें.
हाँ, सवाल क्या है? सॉरी, से दैट अगेन.
आपने W22 को 1 लिया हुआ है.
W22 को मैंने
The weight is 1 here.
No, the weight is not 1. This is an unknown. An initial, it's some guess that we have. So remember, when you start off a neural network, what you do is you start off with random values of all the weights. W11 से लेकर के W1n तक, and all of these weights are going to be randomly chosen. They're going to be some completely random value, maybe between -1 and +1, or it could be alternatively chosen. The biases are also going to be all randomly chosen. All of these are going to be random. You don't know this. This is like when a baby is born, all right? A human baby or an animal baby, उसके जो brains में जो synapses होते हैं, those are not pre-programmed. Well, there is some हमारे पास अंदर एक कुछ चीजें हमारी pre-programmed होती हैं, right? I mean, when a baby gets hurt, he cries, he or she cries, right? That's pre-programmed. So those neurons are already there. However, the neurons to actually understand an image, right, or to be understand कि भाई आग में हाथ नहीं डालना है, fire is hurtful, that is not programmed. So in a brain, there will be some portions of the neural network which is going to have some weights which come in from as part of the genes perhaps, okay, and some portion which is going to be learned, okay. So the learned portion is going to be completely random, and that's going to be trained as the baby or as the the robot gets trained over a series of iterations. As it learns, it sees the output and it says, well, this output is not making sense. It's going to calculate an error, and then slowly the through the iterations, you're going to try to train the neural network and try to improve the weights. Now, in all of this, what is key? If you want to train this neural network, can we train? How do we? What is key in all of this? How do those weights get updated? The error. To be able to calculate the error, what do you need? You need the inputs and the output. The label data is critical. So this is an example of supervised learning. This is not unsupervised learning. In other words, you need to have data which is labeled, and labeled data is not easy to get. All right. So imagine that you're doing a self-driving car. You give it a certain input. Now you have to steer the car, and the car needs to figure out, okay, bhai, agar red signal aaya hai, so do I need to stop? Do I need to press the brakes, or do I need to speed up? Right? If the road is turning towards the right, do I need to make a left turn, or do I need to make a right turn, or do I need to go straight? So somebody has to actually give the system a whole series of label data. And that's extremely difficult. Imagine that you've got thousands of images coming in, thousands or millions or billions of data coming in. Somebody has to very painstakingly go ahead and label all the data. All right. Unless you do that, the neural network is not going to work. However, of course, there are some networks, and you've seen those, some precursor of that, which don't require label data. Okay, and we'll study those later on. But right now we're talking about those neural networks which do require label data, and those are supervised training. Okay. So somebody has to do all the labeling, and once you've got a bunch of large number of data, and the other thing that requires is a very large amount of data, because they can, as soon as you do the first iteration, the weights are not going to be very fantastically accurate. Okay, you have to give it a whole bunch of new data, and then train it again. Okay, give another set of data and keep training. So the iteration has to keep on going, on and on. Yes, it will have to be supervised learning, because what you could do is, if you want to train dogs and cats, what you'll do is you'll provide a whole bunch of data. So these could be images, and we'll talk about this later on. So it's a bit jumping the gun, but this would be data of an image of cats. Okay, and for all the cats images, you expect that the output will be 0. All right, and then you'll give it a whole bunch of labeled data of dogs. And you will say, well, whenever you get an image of a dog, this output, the labeled data, will be a 1. And then you'll calculate the error. And so slowly over a large number of data, your weights will get slowly trained, and they'll get better and better. Now, if you've done thousands and millions of iterations and thousands of millions of images, hopefully you'll have a network which is so well trained that as soon as you give it a new image of a cat, it will immediately say, with a certain degree of accuracy, of course, there'll be certain possibility of error still there. It will say that this is most likely with a 95% probability, let's say, that it's a cat. Okay, and if you give it an image of a dog, it will say with a 94% accuracy, this is a dog. Yeah. So that's different. Okay, so that was an example of unsupervised learning, where it was able to actually differentiate different images, and it did this by clustering. So in clustering, what is happening is basically you're saying, okay, ye jo data hai, this is a bunch of cats and these are a bunch of dogs. It doesn't know that those are the cats and dogs. All it knows is that there are some features which basically cluster this. Okay, and there are some features which are basically clustering this. Okay, and that's unsupervised data. Okay, so we'll talk about all of that a bit later on. So you have to hold on some of those questions for later. जी. आपका सवाल था. Yes, absolutely. So now in the next phase, we'll start talking about how to actually improve the learning rate, okay? Because so far we've studied a very simple algorithm which says that we start off with a particular learning rate and you find the answer. Now in the homework assignment, I've asked you to experiment with this. I've asked you to start with a very small learning rate, 0.00001. Then I've said, okay, what's the largest learning rate? Then try to increase it by, let's say, an order of magnitude. Go with, multiplied by times 10. See, are you converging to a result or not? If you still are, how long does it take you to converge? Now, take another learning rate and multiply it by 10 again. At some point, what's going to happen is the learning rate will become too big. When the learning rate becomes too big, do you think you'll converge? No, you won't converge. You'll start getting numbers which are going to infinity. Okay. So my question in the homework assignment is, at what point, roughly speaking, at what value of R do you actually not get convergence? Okay. So this is what the homework assignment is for you to be able to figure out at what point you get that. So you'll have to experiment with this. Okay. Let's stop over here.